Okay, hello everybody to this week's ISGC seminar talk. Today's speaker is Paolo Pani. He did his PhD in 2011 at the Università di Cagliari, and since 2015 he is a professor at the Sapienza University of Rome, first assistant and associate, and now since 2022 he is a full professor. Thank you very much, Paolo, for agreeing to give this talk. The stage is yours.
Thanks, Torben. Thank you very much for this introduction and the kind invitation. Thanks to all the organizers. It's a pleasure, of course, to give this seminar. So I'm going to talk about black hole mimickers and how to distinguish them from black holes. This talk will be mostly about some sort of personal ideas and ongoing development. So most likely there won't be much overlap with other talks that you had in this nice series of seminars. So you might wonder about the title. So the title is "The Butler Didn't Do It: Some Clues on Black Hole Mimickers," and this is because this talk was based on some discussion that we had during a workshop held at Princeton University in March and organized by this group of people. The workshop was actually very nice and eventually result in a sort of white paper or review paper. It's actually, probably like a sort of opinion paper by these authors here, and you can find it on the archive. And so I was inspired by the nice poster that the organizers decided to use for black hole mimickers. So it's a sort of fingerprint with a black hole at the center, and the topic was precisely to go from theory to observations in the area of black hole mimickers. So this is why I decided to organize the talk and also my contribution to this work as a sort of clue game. I'm sure that you are familiar with that. So essentially there is a killer and you have to essentially investigate which of these people is the killer. So this is why I choose the title, because typically in this like B-movie clue investigations, the butler is typically the killer. So I'll try to argue that sometimes it might not be. And this, of course, is done in the context of black holes and black hole observations. So we know that black holes are now everywhere. From electromagnetic bands, we have evidence for supermassive black holes at the center of our own galaxy and also in other galaxies. And we have several observations of black holes and black hole mergers in the gravitational band, and these observations are actually growing in time. And they were awarded to Nobel Prizes in 2017 and 2020 for both for gravitational waves and electromagnetic black hole observations, respectively. So one natural question is, why are we still testing the nature of black holes? We know nowadays that they are everywhere, which in the context of this clue game can be translated in, why are we still playing clue? We know that the butler did it. So I'll try to argue otherwise, or at least to discuss some clues that can be used to distinguish black holes from, say, black hole impostors or black hole mimickers. And one of the problems is that even though we have very strong evidence that black holes, classical black holes, exist in our universe, there are problems associated with them at the theoretical level that we would like to overcome. So let me just try to motivate this a little bit. So one of the problems is that black holes have a huge entropy. If you compute the Bekenstein-Hawking entropy of a black hole, for example, M87 shown in this famous picture here by the Event Horizon Telescope, you will see that the entropy corresponds to this number of states, so e to the 10 to 95 states. So this is an enormous number, which is in really dramatic contrast with what general relativity predicts, because on the other hand, general relativity predicts that black holes should be essentially unique. They are described just by a bunch of numbers, the mass, the angular momentum, the black hole. So they are almost like elementary particles and describe one state. So probably this discrepancy between the black hole no-hair theorems in general relativity and the huge entropy expected by quantum mechanics is one of the largest discrepancies in physics, and we don't actually understand it. Is also associated with the infamous information loss paradox that essentially tells you that evaporation, black hole evaporation, violates quantum unitarity. So we need to understand, well, the fate of black hole evaporation and what happens at the scale of the horizon. And finally, we know that there are singularities inside black holes, and even though they are not problematic from the point of view of an external observer, they are still problematic from the point of view of the theory, because we know that general relativity eventually must break down inside black holes. So all these are actually fundamental problems that we would like to solve. So if you are optimistic, you might say, well, there are models predicting new physics at the horizon scale that can in principle solve all of these issues, and I will mention this later. And we might actually try to use these models to search for signature of quantum gravity in black holes, even in current observations. If you're more conservative, you may say, well, quantum corrections are negligible, at least outside the horizon, so we don't really care about this phenomenologically. But still, if you really want to test the black hole paradigm, you want a concrete model to compare, especially because, for example, in gravitational wave observations, what we do is a Bayesian model selection between, say, the black hole hypothesis and an alternative hypothesis. I would call these exotic compact objects, or ECOs, and essentially for me would be a compact object that is dark because it's actually pretty compact, so with a large redshift, but without a horizon. And in any case, either if you are optimistic or pessimistic, I think you will agree that black holes are quite unique. They have quite unique properties, and therefore detecting any evidence from departure from the classical black hole picture would be an amazing way to detect either new physics or new matter fields. And well, this was discussed in several reviews mentioned here, and especially in these last two that appeared well, less than 1 year ago. This was a conference in Copenhagen, and this is the workshop at Princeton that was mentioned. So this is the motivation. So we have one suspect, maybe more, in the sense that we might even think that not all dark compact objects in the universe are black holes. Maybe there are other objects together with black holes and neutron stars that we don't have yet discovered. But we want to find some clue for them. And I will discuss three. They are not necessarily like comprehensive, but at least I think it's something interesting to put together and discuss what is the difference between black holes and other objects in terms of the maximum compactness they can reach, the reflectivity and their boundary conditions, and finally the stability, dynamics, and what I would call camouflage in the sense of mimicking black hole aspects in certain contexts. Okay, so let me start with the first clue. I will go clue by clue, let's say. So the first one is, what is the maximum compactness of a dark object? And I will define compactness in the usual way. So it's basically the ratio between the mass of the object and the radius. I will typically use G = 1 units. So really this ratio is dimensionless. And for a Schwarzschild black hole, this is equal to 1/2. Sometimes instead of using this compactness, we can also define this parameter here, epsilon, which is essentially the same quantity. It just tells you, it's a way to parameterize the radius in terms of the Schwarzschild radius of the corresponding black hole. So epsilon, of course, is bigger than 0. And being very small means that the object is very compact, almost as compact as a black hole. Whether if it is larger, it means that the compactness will be smaller. For this analysis, I would mainly focus on spherical symmetry, just because it's easier, and also because we expect that rotation will increase the maximum compactness, but it will not change the picture dramatically. So the question is really, what is the maximum compactness that is achievable in a given theory? And for this, there is a theorem that comes into help, which is Butler theorem, that tells you that under certain hypotheses, the maximum compactness is this number here. So it's actually smaller than the 1/2 of a black hole, and in fact implies that there is a compactness gap between compact objects and black holes. Of course, this is a theorem, so it means that it's based on some hypotheses, and here are listed. So, for example, it assumes perfect fluid, staticity, isotropy, most importantly, general relativity. And well, it also tells you how you can possibly evade this theorem by relaxing each one of these hypotheses, or maybe multiple of them. In particular, we'll focus on the hypothesis of perfect fluid, isotropy, and classical GR, as these are the three main ways we can try to evade Bugdal theorem, so evade one of these hypotheses. So let me give you some examples, very say quickly without entering details, really just as representative of classes of exotic compact objects. Probably the most famous one are boson stars. So boson stars are soliton, essentially solitonic solutions to GR coupled to a complex scalar field, minimally coupled to a complex scalar field. There might be self-interactions, so there is a mass term plus potentially self-interactions, and they have a maximum mass and a compactness that depends strongly on these coupling parameters here. So they exist as regular solutions with a non-trivial scalar profile. And an interesting question is, this is a scalar field, it's not a perfect fluid, and in particular, a scalar field behaves as an anisotropic fluid. So you might ask yourself whether you can beat Bugdal bound or not. So there is actually a simple argument to show that you can never really exceed the Bugdal bound, and the reason is the maximum mass and compactness increase with self-interactions, means the bigger these numbers, the bigger the maximum mass and compactness. But if you look at the equations, at least in spherical symmetry, you see that the radial pressure and the tangential pressure have this expression here. Omega is the frequency of the scalar field that is oscillating, so it's a phase. And as you can see, when the potential becomes dominant, so when it is much larger than these quantities here, the tangential and radial pressure are equal to each other. So essentially, this means that in the large self-interaction limit, where the object is very compact, eventually the scalar field behaves like an isotropic fluid. And for isotropic fluids, we know that there is a bound, it's typically called causal Bugdal bound, and is obtained by requiring that there is a perfect isotropic fluid with the most extreme equational state you can conceive. And this equational state is this one here, when P and ρ are linear, meaning that the speed of sound is equal to the speed of light. In this case, you can show that the maximum compactness is this number. So it's actually much smaller than Bugdal, and it cannot be actually exceeded by any isotropic fluid. And the conjecture is that for boson stars, it would be the same, because this self-interaction makes this approximately isotropic fluid. The second category, therefore, are anisotropic fluids, and there is a covariant way to build anisotropic fluids in GR, essentially by writing a stress energy tensor, which is the isotropic part, plus these extra pieces that essentially parameterize the pressures in different directions. These models satisfy some of the energy conditions, the weak and the strong. In the highly anisotropic case, they violate the dominant energy condition and also causality, meaning that the speed of sound can be actually higher than the speed of light. But the trend that you get in the mass radius diagram is the following. So if you have a standard isotropic star, like a neutron star of this shape, when you increase anisotropy, your mass radius diagram tends to move on the right and also exceed both the photon sphere. So these objects can have a light ring at 3m outside the object, which does not happen for neutron stars, but it can also exceed the Bugdal bound, as you can see. Actually, these objects can be as compact as black holes at the price of violating the dominant energy condition and causality. So this brings to a class of larger objects that typically are called relativistic elastic stars, in which you can introduce anisotropy in a coherent way. And the way to do that is to prescribe an energy density functional, which acts as your equational state in general. And from this function, you can compute the radial pressure and the tangential pressure in a self-consistent way. And this, of course, includes also the case of isotropic fluid. And then the question is, what is the maximum compactness of these objects? So you can show, as shown in this diagram here, this is the maximum compactness as a function of one of these elastic parameters. It's called Lamé parameter. So you can show that there are models like this green line here they can be as compact as black holes, or black hole is here at 0.5, and in these models you can reach this compactness. However, if you require all speed of sounds, characteristic speeds to be smaller than the speed of light, so essentially you require causality, therefore the maximum compactness you get is actually smaller than the black hole bound. So there is this gap imposed by causality of matter. One has to be careful because in these models there are several speed of sounds depending on the way perturbations can propagate in the fluid. So to summarize, what you can have in these most general models is the fact that they can reach the black hole limit. Sorry, yeah, they can reach the black hole limit in certain conditions, but when you require causality, which sometimes is called for physically admissible models, then the maximum compactness is this number here, which is conjectured to be the maximum compactness of any elastic object in general relativity. On top of that, it's not guaranteed that these models are stable. You should also require stability, at least for radial perturbations, which essentially means that in this mass radius diagram, you are below the maximum mass, so in this stable branch here. And this imposes a further condition on the compactness, and the final number that you get is this one here. So it's bigger than the causal Bookdal bound I mentioned before, but it's smaller than even the Bookdal bound in a perfect fluid. So the bottom line is that requiring stability and causality limits the maximum compactness that you can have. It's also interesting to note that, so one crucial property of black holes is that they have an arbitrary mass. So the mass is a free parameter in the Schwarzschild solution, which is very hard to mimic in any other object. For example, boson stars have a mass dictated by the Lagrangian of the scalar interactions. So in order, if you really want to mimic a black hole, say from stellar objects to supermassive ones with the same model, you necessarily need a scale invariant solution. And there are no scale invariant solutions in general relativity for perfect fluids. Interesting enough, if you allow for anisotropies, you can have them. So you can construct an anisotropic equation of state for which the mass radius diagram is linear, is exactly linear, meaning that this object will exist with any mass and any radius. Their compactness, though, is still bounded from above. And the maximum compactness of a physically admissible, stable scale invariant solution is this number here. It's curious that this number is very close to what the light ring compactness will be. That will be 1/3. And well, maybe this is something interesting to understand here. But the point is that anisotropies are very important to build ultra-compact objects. However, viable models always have a compactness gap with respect to black holes, at least in general relativity. So, and this brings to the third and last category I want to discuss, which is going beyond general relativity. And I will take this example as an example, black hole microstates, which I think are very relevant for various reasons. Well, first, because they are solutions to typically supergravity theory or low energy truncation string theory. So you can take them as solutions beyond general relativity. But on top of that, they essentially are a proxy for the idea of fuzzballs replacing black holes. And the idea is that black holes should be quantum objects whose entropy is actually accounted for by a huge number of regular horizonless microstates that should, in fact, count the degrees of freedom, the fundamental degrees of freedom of a black hole. So interesting enough, in these theories, there are very big families of solutions which potentially can describe all the entropy of a black hole in certain controlled settings. This has been proved rigorously. And from, say, classical theory, they are solutions, solitonic solutions with GR coupled to scalar and gauge fields. So the nice thing of this model is that, well, it's a top-down approach, meaning that you really start with a fundamental theory, which is well motivated, and in principle, it will solve in one go the horizon problem, so the entropy problem of black holes, the information loss paradox, because these objects are horizonless, and for free, they are also regular. So they don't have the singularity that black holes have, they end up in a regular cap. In addition, the mass of the solution is a free parameter, just like black holes, so they can well describe either stellar or supermassive objects. And a key feature of these solutions, I will discuss this later, is that they live intrinsically in higher dimension with non-trivial topologies. And when you compactify these in 4 dimensions, because eventually you want to describe 4-dimensional universe, it turns out that they have very unusual, sometimes even pathological problems, which are a byproduct of the compactification. So in 5D, for example, these are perfectly fine, while in 4D they might appear as singular solution. And this sort of challenges the standard way one builds educated models in 4 dimensions, because it's a nice way to essentially evade some of the hypotheses of known theorems, for example, booked out. On the other side, they are very complicated typically. Sometimes they are not only for extremal or supersymmetric solutions, even though there's been a lot of progress recently on this. And it's also unclear whether studying each of these microstates for the black hole is actually a good indication or a good representative case for an ordinary black hole. So it's the problem of whether these are typical or atypical states. Nevertheless, because of the strong motivation for this model, there's been a growing interest in their phenomenology, and I will discuss this in some more detail later on. Let me just give you an example of how the fact that an object can be particular from a 4-dimensional point of view affects the phenomenology. An example is the multipolar structure. So we know that the multiple moments of an object enters the waveform of a binary system, in particular a second post-Newtonian order. And in general relativity, we know the black holes satisfy this beautiful relation between the mass moments, the spin moments, or the current moments, and the mass and the spin of the black hole. So everything is detected by the mass and spin of a Kerr black hole. For a non-Kerr object, we expect corrections in terms of some deviations from the Kerr multiple moments. Interesting enough, under certain mild assumptions, you expect these corrections when you approach the black hole limit. So as the compactness approaches the black hole value, these corrections should scale logarithmically with this parameter here, the compactness parameter, which is actually good because it means that they are not extremely small, even when this compactness parameter is very close to the black hole. But on top of that, it happens that in some cases, for example, fuzzballs, you might actually break symmetries that exist in Kerr and have a richer structure. For example, you can break equatorial symmetry, have a current quadrupole or a mass octupole that are exactly 0 in Kerr, or even break axial symmetry. So if the Kerr, say, embedding diagram is something like this, where the colors represent the current moments, for one of these microstate solutions, you can break axial symmetry, so you have really a deformed object with all towers of multiple moments beyond the Kerr symmetries. And therefore, recently there has been some interest in trying to extend, for example, waveform models to include all these new multiple moments that are actually absent in general relativity. So to summarize, our 3 say suspects in this clue game can be roughly categorized either as sort of boson star-like behavior, anisotropic stars within general relativity, or some solitons beyond general relativity. They have pros and cons. And well, I just want to advertise that there are these different categories with different properties. So let me now move to the second clue. And well, if you have any question, feel free to interrupt me and ask. So the second clue is about reflectivity of a dark object. So what is the reflectivity, and does it matter? So one important point is that we know that classical black holes are probably the only perfect absorbers we know in the universe. And by perfect absorber, I mean something very standard. Imagine gravitational waves passing through from right to the left. For a black hole, these gravitational waves are perfectly absorbed, in fact, so nothing comes out after this scattering process because these are absorbed by a black hole. If you take a star, for example, a perfect fluid star, the star material interacts very little with gravitational waves, so it means the gravitational wave will just pass through the star almost without being damped. And I would call this perfect reflection. This is perfect absorption, this is perfect reflection. The reason why you call it reflection is because if you look at this problem from a one-dimensional, say, spherically symmetric perspective, these waves feel an effective potential, which for a black hole has this shape here. The horizon is typically at -infinity in this coordinate. And therefore, anything that goes through this potential eventually goes into the horizon. Nothing comes back. If you look at this problem in a one-dimensional perspective, you will get a effective potential of this form, because at the center of the star there is a centrifugal barrier. So you will see that any radiation that goes here eventually comes back reflected. Of course, it does not mean that this object is a mirror. It just means that things go through. Okay. So it's an important point, I think, to keep in mind that perfect reflectivity in this context means no interaction with gravitational waves, which is actually the rule for ordinary matter rather than the exception. So black holes in this case are really the exception compared to any other object that we know of. So how do we use this information? Well, essentially this means that the boundary condition of our perturbation would be different between the black hole case and the, say, whatever other case. And this affects the waveform, for example, in a binary system. And this is shown here qualitatively when we compare two waveforms, one that is dephased against the other. And the reason is that as the two objects approach each other, there may be different effects. For example, different tidal interaction, different absorption effects due to the presence or absence of an horizon, and finally, even a different ring down and post-merger phases that I will discuss in a moment. All of this depends on the boundary conditions and therefore on the reflectivity of the object. So let me focus for a moment on the ring down, so the final part of the merger, in particular the quasi-normal modes. So the quasi-normal modes are defined as the eigenvalue of this linearized equation coming from Einstein's equations. For a black hole, you have this effective potential. The horizon is here at -infinity, and in fact, radiation takes infinite time to get there. And I was mentioning before, black holes are the only classical absorbers, while for any other object, you expect some radiation back. Even if it's very small, the interaction with gravitational waves, this reflectivity would be maybe very close to unity, but most of the radiation will be actually reflected. And this will modify the ring down, but in a very subtle way. In particular, if you look at the time domain signal, so the time domain response of a black hole compared to a mimicker, you will see that initially the response is universal. It does not depend on the reflectivity nor on the boundary condition. And the reason is that this part of the signal is due to the perturbation of this barrier, which roughly corresponds to the light ring of the object. So if the object has a light ring, if it is compact enough, these two potential barriers will be very, very similar. However, in the black hole case, whatever happens here eventually dies off exponentially. In the other case, as you see here, it will be reflected back and may be trapped within this cavity and occasionally tunneled through the potential, which is why you see these post-merger features called echoes that are essentially the prompt ring down reprocessed by this potential barrier, which acts as a filter. So the location of these echoes, the time delay, depends once again exponentially, logarithmically with the compactness, meaning that even if the compactness is super large, the delay will not be that large. And this is why it's interesting from the phenomenology point of view to look at these effects. There's been a lot of searches for echoes in current signals. So far, the outcome, I think, is that there is no statistical evidence, despite some contrasting results. But this has motivated a lot of progress in modeling and searches. And I have to stress that searches right now are based only on toy models, so there is no top-down approach from a fundamental theory, and even these sort of things are essentially done by imposing by hand boundary conditions. And I will show you later actually a more sophisticated model. Let me just mention that the absence or presence of horizon changes dramatically the waveform. In particular, if you consider what is called tidal heating. So tidal heating is essentially the fact that black holes absorb radiation, and therefore this accounts for an energy loss during the spiral, while other objects might not actually be as efficient as in absorbing radiation. What I'm showing here is the energy flux as a function of the orbital frequency in an extreme acceleration spiral, so a point particle orbiting around a supermassive object. So you see two features. So one is that the energy flux is typically smaller than in the black hole case because there might not be absorption on the horizon. It can also be resonantly excited because you can excite the cavity modes I was mentioning before. And what I'm showing here is the mismatch between waveforms with and without this effect. So for a black hole or for any other object. So the striking result here is that the difference in waveform is sufficiently strong because the dephasing is sufficiently large that most likely you can put a constraint at the level of 10 to minus 8 on the reflectivity. And remember that for a black hole, reflectivity is 0, for a neutron star, reflectivity is 1. So essentially these constraints that can be put in the future, for example, with the space mission LISA, will exclude anything else other than the black hole, essentially. Another important fact related with tidal response of objects compared to the black hole case is what is called the tidal deformability of the law of numbers. So the law of numbers are essentially the deformation of a black hole, of an object immersed in a tidal field. And it turns out that for isolated black holes in general relativity, the law of number is exactly 0. So this is a classical result in general relativity. However, this is not true in any other case. So either if your object is not a black hole, or if GR is violated, or if your black hole in GR is surrounded by matter. And in many models of black hole mimickers, the law of numbers again scales logarithmically. So there is this logarithmic behavior in the black hole limit that is almost ubiquitous in all the observables that we can have. And let me just stress that any evidence of log number different from 0 in an object that is too massive to be a neutron star would imply a departure from the classical vacuum GR black hole picture. So it would be a smoking gun for new physics, essentially. And this is why actually in current and future observations, testing this property would be very important. So it would be interesting also to study in a sort of model independent way the response, the tidal response of an object. And this was done recently in this paper here with some collaborators by modeling the reflectivity that I mentioned before at small frequency, because the law of number is actually a low frequency, almost static observable. So if you expand the reflectivity in this way, so it's a 0 order and a first order in frequency term, it turns out that you find 0 log number whenever this reflectivity is actually, this coefficient is actually unity, which makes sense because essentially it tells you that only if your black hole is a perfect absorber, a perfect reflector, let's say at 0 frequency, then you will get a different response. And in fact, it turns out that the log number, that I call it K2, depends on this coefficient, so the linear in frequency dependent reflectivity. And again, you find this logarithmic correction in the black hole limit. So whenever this epsilon is sufficiently small, you find that the log number goes to 0 as in the black hole case, but only logarithmically. So again, it's a small quantity, but not extremely small. And well, in this study also we found a lot of interesting effects, for example, resonances in the dynamical of number that you can get at finite frequency and so on and so forth. But I think this is the main result of the work. So very recently, with the same collaborators in a paper that will appear probably next week, we are generalizing this using the so-called membrane paradigm. And the idea is that instead of using the reflectivity, one can replace an ultra-compact object by a membrane, and imposing the properties of this membrane, in particular its bulk and shear viscosity, in order to mimic the ultra-compact object. And you can play the same game with a black hole, and in fact there is a very famous black hole membrane paradigm in which the horizon properties are mapped in terms of a membrane. And in particular, you see that the reflectivity can be written in this form. The viscosity parameter of a black hole is actually 1 divided by 16 pi, so it's a given number, pretty high, by the way. And whenever the viscosity of your object equals the one of a black hole, you get zero reflectivity, otherwise you get a different number. So for a perfectly non-viscous object, eta will be zero, and therefore you get reflectivity equal to 1, as it should be for a perfectly reflecting object. So again, you can expand the reflectivities, both bulk and shear viscosity, in frequencies. And it turns out that the log number, there is an analytical expression for the log number depending on eta, zeta, so the two viscosities, and the compactness. And this is valid for all particular cases we know of: black holes, wormholes, any exotic compact objects, graviton stars, even neutron stars. And in fact, for neutron stars, what we are finding is a very interesting universal relation between these coefficients here, so the shear viscosities for L equal 2 and L equal 3, they are very much independent of the equation of states at the level of 1%. This is very similar to the quasi-universal relations for neutron stars found in other works, in particular by Yagi and Younes more than 10 years ago, and they also apply for different multiple law of relations. So it's a generalization of that in the context of the membrane paradigm. Okay, so let me move to the last clue, which is very important. So suppose that you have an object that is very compact and almost as with a reflectivity almost as small as the zero reflectivity of a black hole. So can we use it as a good black hole mimickers? Of course, the question is that object dynamically viable, meaning it is stable, and how does it react from external perturbations? So some years ago, we studied this problem for the microstates I was mentioning before, so fuzzballs, in particular studying the dynamics of a test scalar field of one of these geometries. As I mentioned before, these geometries are very complicated. The shape is very irregular, not very symmetric. And you can compare this with the black hole case. So the first line, these are 3+1 simulations done in this paper here. So the first line is the response of a black hole to a spherical perturbation. So everything remains spherical, and after a certain time dies off completely. The second and third line is the response of one of these guys without an horizon, and you see two things. So the first one is that you start with a spherical wave packet, and eventually you develop some funny shapes because of the breaking of the symmetries. And the second fact is that at later times, while for a black hole there is nothing, in this case there is still radiation. And the reason is that for a black hole, everything decays exponentially, dies off as a rain down. For this object, the absence of the horizon gives you a much long-lived signal that in fact exists and decays much more slowly than in the black hole case. You also see the typical echoes I was mentioning before, but because of mode mixing in this case, the signal is much less clean than it was in toy models. So this also tells you that studying realistic models may complicate the signal quite significantly. So based on this, recently there is quite a lot of interest in trying to understand this problem in the context of a more workable theory and model of microstates. And in particular, I find very interesting these topological star solutions found in this paper by Heidmann a few years ago. So these are, the idea of this solution is to try to preserve certain key aspects of the fuzzball paradigm, but make it simpler. So in particular, find horizonless smooth solutions in a theory of GR in higher dimensions with non-trivial topologies, and hopefully find easier solutions to study, and in particular to study their stability, for example, or their dynamics. So in the last part of this talk, I will discuss something related with these topological stars. So very briefly, they are solutions to 5-dimensional general activity coupled to a gauge field. They are regular solutions in 5D. I mean, you can read the solution here. Is actually very simple. Of course, we are interested in 4 dimensions, so you can compactify this theory in 4D, and you end up with Einstein-Maxwell-Dilaton theory with 2 Maxwell fields and 2 Dilaton fields. So it might look complicated, but it's in fact a theory that is GR coupled to matter. So for example, it has a nice initial value problem, is well posed, and so on and so forth. So you can study it at fully nonlinear level. When you compactify to 4D, the same solution, which is regular in 5D, actually is singular with a curvature singularity in 5D, happening when this function fb, which is just 1 minus rb divided by r, is 0. And at the same point, the Kaluza-Klein scalar field diverges, and this divergence is really only due to the compactification. When you work in 5D, it's perfectly fine. And here I think is also an interesting point that if you take the solution in 4D and you don't know that it comes from a 5-dimensional embedding, you will just classify it as pathological. But in fact, it's not. You can study perturbation of this solution and from the 5D perspective, compute the boundary conditions at the singularity, because there, I mean, you have a regular solution in 5D. The parameter space of this solution is very interesting. Everything depends on this radius, on this ratio here. When the ratio is smaller than unity, you have black holes with a magnetic charge. When the ratio is bigger than unity, you have these topological stars, which do not have an horizon. The charge mass ratio is this one here. And there is a point here where the two solutions coexist. So they have a similar or even equal charge to mass ratio. So it turns out that in certain regimes, in particular down here and up here, so for smaller value or very large value of this ratio, the solutions are unstable with a typical instability very similar to the Gregory-Laflamme instability. But there is a region in between in which they are stable in principle, and they interpolate between black holes here and objects that can be more or less compact depending on their properties. In particular, they can have an unstable photon sphere like a black hole, but even a stable one if they are sufficiently compact, and therefore they classify as ultra-compact objects. So recently, with these people here in this project and also some other independent group, we studied the perturbation of these objects at the linear level. In some cases, the perturbation can be recast in a Schrödinger-like equation with an effective potential. And this is the effective potential for the black hole. This is the effective potential for topological stars. You see, when the star is not very compact, you just get this shape here. When it's very compact, you get an unstable light ring corresponding roughly to this maximum, and then a cavity here developing between the maximum and the center of the star. And you can work out the boundary conditions for this problem from the 5-dimensional perspective. So in work led by Alex Dima and Marco Melis in the last year or so, we studied the perturbations and the quasi-normal modes of the system. So interesting enough, if you look at this real and imaginary part of the quasi-normal modes, you will see that depending on where you are in parameter space, the imaginary part can be black hole-like, so relatively large, and this corresponds essentially to the W modes of a neutron star, for example. But as the compactness increases, you will move down into this region here, and you can check that this is a logarithmic scale. So the imaginary part of this frequency becomes very small. And these are precisely the long-lived modes I was mentioning before that are supposed to give rise to echoes. And in fact, this is what we obtained in certain cases. So if the topological star is sufficiently compact, the prompt ring down is universal, is the same as the black hole, but then you get other features later in time due to the excitation of these long-lived modes. And as a bonus, we also test the linear stability of this problem. So in this parameter space, these solutions are perfectly stable. Perturbations decay slowly in time, but still decay. And you might get situations, for example, here in which the topological star and the black hole have very similar effective potential, and therefore very similar properties at large distances, but still the response at later times is actually different. And let me just mention that everything I said before is valid at linearized level. Recently, with these people in Rome, we are studying also a similar theory, a fully nonlinear level. So in this theory, there are hairy black holes, so black holes with a non-trivial scalar profile and a given, say, electromagnetic charge. In certain region of the parameter space, the effective potential that you get is this very funny shape. And what happens is that in this theory, precisely because it's well posed and you can study it at fully nonlinear level, you may ask yourself what happens to perturbations which are not small and still excite these black holes. What I'm showing here is the response, not the linear one, the fully nonlinear response of a black hole to a spherical perturbation of the scalar field done in numerical relativity. In this particular simulation, the black hole horizon has grown by 30 times, so it's completely nonlinear, and still you see that there are hints of echoes in this case. Of course, these are black holes, they are not like regular solitons, but we expect very similar results also for regular microstates, in which instead of an horizon, you still have this property here for a black hole. And well, the advertise I want to make is for exotic compact objects, it's very hard typically to do nonlinear simulations. Within this theory, this is actually possible. So I would say stay tuned for further development. I think they would be interesting. Okay, so this brings me to my conclusion. I hope I convinced you that black holes are very special. They have very special properties in terms of multipolar structures, tidal deformabilities, and ring down features and compactness. And in testing them, even just at a theoretical level, can reveal deep properties within GR. For example, the fact that ordinary matter has a gap, compactness gap, between, say, regular objects and black holes. Reflectivity is very different between black holes and other objects, but it might actually not be that relevant because in the large compactness limit, eventually the phenomenology seems to approach the black hole one, even though sometimes it does that logarithmically, which is a good feature if you want to put constraints on your model or to detect anything. And well, very recently, there has been a lot of progress in building top-down models for black hole mimickers with highly unusual features. So these are actually, I would say, a good starting point to bring this to the next level. And there's been a lot of progress in understanding the phenomenology in terms of ring down, multipolar structure, tidal effects, and how these affect the waveforms. So I will finish by saying that taken individually, it's actually easy to cook up single effects and smoking guns, but actually it's much harder to find a coherent model which is viable from the physical point of view and actually contains all these features, so it should also be easily can be more easily falsifiable and highly constrainable. And this is actually what we are currently working on. So finding consistent models, studying their nonlinear dynamics. So far, almost only boson stars can be studied at the fully nonlinear level, so it's important to extend this with the final goal of finding realistic merger waveforms. So again, if you are very optimistic, you may say this will be our route to observatory signature of quantum black holes, maybe. But even if you are not that optimistic, I think it's important to model this now. And essentially, the motivation is that the constraint that we're going to get, either with current observations and more importantly, the future ones, will be unparalleled in the sense that it will be the stronger constraints we can hope to put on horizon scale physics in the next decade. So it would be very important to model this and look at what the data has to say. Of course, we cannot neglect the possibility that, as like in all these detective B movies, eventually, even if it's a boring ending, maybe the Butler did. So eventually, maybe all these compact objects are black holes. But it's a possibility that would still be very interesting to prove. Okay, so I thank you for the attention, and well, I'm happy to take questions.
Thank you, Paolo, for this really nice talk. Are there questions? Geo?
Oh, yes. Thank you, Paolo. Very nice to see you here. So I actually have two questions. So the first question is about, like, in the conclusion, you say that the reflectivity doesn't matter in the black hole limits. Can you elaborate more on this? Maybe I missed a bit.
Yeah, so it's something that can be seen, for example, either in the it can be seen in most of the observable, but for example, take this log number here. So the reflectivity does affect the log number in terms of this coefficient here that enters the final result. But imagine that your object is very, very compact. Eventually, this part here will dominate. So what this is telling you is that regardless of the reflectivity of the object, it can even be a perfect reflector. The log number will go to zero logarithmically approaching the black hole limit. So you can mimic the black hole type of deformability even if your object is perfectly reflective. And something similar happens also in the ring down, in the sense that if your reflectivity is, even if your reflectivity is unity, so very different from the black hole case, if the compactness is large enough, approaching the black hole limit, all these echoes will be postponed later in time. So you will be like fooled to think that this signal is the same as a black hole, just because your time scale for the observation is small. So regardless of the reflectivity, if the compactness is large enough, essentially big redshift can mimic the black hole phenomenology. That's what
I see. Thank you very much. Or maybe I ask the second question. I don't know whether there are others.
I don't see any right now.
Okay, so the second question is about, so you mentioned about the scale invariance. So I understand the logic that if you have compared objects that are scale invariant, then you are going to have a linear mass radius relation. This I understand. So my question is about the opposite. Is the opposite also true? Like if I have a model and in some certain parameter range, I also have a approximated linear mass radius relation. Can I say this model is also scale invariant in that parameter space?
Yeah, I never thought about that. Naively, I would say yes. Yes, I would say so, because in a scale invariant model, you just have one parameter, which is the central density. And what should happen is that if you rescale the central density by, say, a given amount, both the radius and the mass scales accordingly with some rescaling factor, but you remain in the same line in the case. So I think that even if this happens only, say, in a given regime, so not everywhere, I think it will work, yes. Of course, the main problem is you will need a model in which these regimes span several orders of magnitude, because, I mean, if you really want, say, to describe with the same model, say, a 1 solar mass object and a 10 to 9 solar mass objects, then you need 9 orders of magnitude in which this mass radius relation is linear. But yes, I think that if you can find it when it's linear, it should work.
I see. Okay. Okay, thank you.
Sure.
Any other questions? Maybe I have one. So right now you more looked on the gravitational wave part. Did you also already look at the photon rings?
But personally, not that much. There has been, yes, studies in this respect. In particular, I think I don't have in the backup slide, but for fuzzballs, there has been studies in order to understand, say, the shadows and even accretion around them. I think there are several interesting things there. So one is, if you really just take the object and look at the shadow, again, because of large redshift factor, it can happen that the shape of the shadow is very similar, even though the object eventually is not absorbing radiation. On the other hand, you might expect certain of these models to have an effective absorption due to various reasons. In fuzzballs, this is very natural because you have a lot of states which are almost degenerate in energy. So it's actually very easy to absorb photons. And that actually makes the shadow even closer to a black hole. I think that an important point that I didn't touch upon here, but I think it should be important, related to accretion is if you, instead of just looking at the shadow, you think that, I don't know, the objects that we are seeing are actually staying there for millions of years, even more, they have been accreting forever. And so the question is, for example, if you take a boson star, what happens to the material that is accreted? For a black hole, it goes into the horizon and the black hole grows. For a boson star, in the simplest model, if the boson does not interact with matter, matter should start accumulating inside the boson star. And this has been discussed in certain cases, and it shows that the accretion features that you get in terms of the image that comes from the object is different, and might also this matter accumulated inside the object might also drive some instabilities, or for example, matter collapse inside the object. Like all this matter goes into the boson star and eventually collapse to a black hole, and the black hole eats the boson star itself. So this kind of studies has been done in certain cases. I think it would be interesting to understand in others.
Okay, thank you. Are there other questions? If not, I would suggest to end the recording here. Thank you very much, Paolo, for the talk.